Hi, everyone. Thank you for joining us for this workshop. Today, we want to tell you about quantum orchestration, which is what we're developing at Quantum Machines. And we want to tell you why we believe that this is a new paradigm for quantum control, and why we believe this can make an important impact on quantum research and on the quantum community. So a good place to start is to ask why. Why do we believe that we need a new paradigm in quantum control? So at Quantum Machines, we are a team of physicists and engineers, and we have people on the team who worked on almost any quantum system out there: trapped ions, neutral atoms, superconducting qubits, quantum dots, NV centers, etc., etc. And we've been working with these quantum systems for many years. And we all know that in order to do something interesting with these systems, or in order for these quantum systems to do something interesting for us, we need to always orchestrate a very complicated sequence of control and also measurement signals. And this complicated sequence of control and measurement signals is always being orchestrated by a classical system. And of course, if you go to any of your favorite quantum research labs, you're not going to see such a nice classical orchestra, but what you are definitely going to see is a pile of test equipment. So AWGs, lock-in amplifiers, digitizers, signal generators, spectrum analyzers, etc. And while this test equipment was really great and did the job up until several years ago, as experiments started to become more complicated, sometimes experiments with many qubits, sometimes experiments requiring real-time feedback. So as the sequences of control and measurement signals became more and more complicated, this test equipment was simply not good enough for the job anymore. So it's not good enough anymore for labs working on developing the next generation basic building blocks for quantum computers, exploring complex control sequences for better control, better error mitigation, better error correction, etc. And it's also not good for scaling up and building useful large-scale quantum computers, where systems of hundreds and also thousands of control and measurement channels must be programmed in a coherent way and must be fully synchronized, and where classical computation must be done in specialized hardware in real time, and where all of the modules across the system, the control system, must communicate with one another with very low feedback or very low latency in general. So as we looked at the existing control equipment and control systems, we saw that the existing solutions typically cost years of development. They result in suboptimal systems with sometimes exploding runtimes. And there is no way to perform completely general feedback with completely general processing between measurements and feedback response, and which is something that we believe is going to be an essential component and play an essential role in the future of the field. And finally, and very, very importantly, it is very difficult and very cumbersome to program experiments with the existing control solutions. And that's why we thought that there needs to be a new paradigm in quantum control, and that's why we developed the Quantum Orchestration Platform. So what the Quantum Orchestration Platform is, it's a fully integrated hardware and software system that allows you to do three things, essentially. First, it allows you to run the most advanced quantum experiments, any experiment, any quantum control protocol that you can think of with the right performance. It allows you to do so. Second, it allows you to run these experiments on any number of qubits. And finally, you can do it all from a very super intuitive programming language that we call Qua. So each and every one of those may sound simple, but definitely when you combine these together, when you want to run from a super intuitive programming language, any complex control sequence on any number of qubits, that starts to become a very difficult problem. So what makes this possible in the Quantum Orchestration Platform? Well, so the first thing that we did, we developed dedicated hardware right here. The hardware has an analog front end with many channels, many input, output channels, digital, analog channels that are all synchronized and all operate as a single unit. And then at the heart of this dedicated hardware, we have the most important part of our technology, which is our pulse processor. So this is a true new kind of processor, not an improved measurement device. It's really a new kind of processor, just like the Intel processor or the GPU in your computer. This is a new kind of processor with a unique architecture and an instruction set. The instruction set meaning the language that the processor can digest, the language that the processor can run, which is designed specifically and optimized specifically for quantum control. So the processor allows combining together in a unique way the four elements that we believe that form any quantum control protocol. So what are these four elements? The first one is waveform generation. So this is generating the pulses that perform the operations on the quantum device, and as well as reshaping their many parameters in real time. So this is a very important capability, the reshaping of waveforms in real time, because the processor can do more than just changing a global amplitude of a channel or something like that. It can really change the parameters of each and every pulse, including stretching pulses in real time, composing pulses from basis waveforms, changing phases, frequencies, chirping frequencies, etc. And it can also do all of that based on measurement results. So this is where feedback comes in. The second element of the pulse processor is the waveform acquisition. So measuring signals from the system and processing them. And this includes many different processes from simple demodulation and integration of analog signals, time tagging of digital signals, counting of digital signals, applying neural networks to your input signals, etc., etc. Then the third component is the classical processing. And this is where this is truly different from any other device because you can perform completely general classical processing. So this goes from general classical processing on the measurements, on the acquired signals. This can go for tracking errors, for error correction, performing real-time Bayesian estimations of parameters, simply scanning pulse parameters, changing an amplitude of a pulse to the amplitude that it was before plus something. All of this is classical processing, and you can do it with the pulse processor in the most general sense. And finally, the element that completes the picture here is control flow. So if else statements, loops, for, while loops, switch cases, and all the good stuff. So you can have most general control flow with branching, and then all of these together span a phase space of what you can run with the pulse processor, okay? So you can compose from commands involving waveform generation, waveform acquisition, classical processing, and control flow. You can compose your control sequence. And this, of course, needs to be scaled by the number of channels that you need to control, or the number of qubits that you have in your system. All right, so here is the pulse processor. It's actually composed of many pulsar cores, what we call pulsar cores. These are the cores of our processor, and they can do all of these different elements as well as communicate between one another, and they can communicate between another across processors. So if you have many pulse processors, they can communicate as a single pulse processor. And so this is the heart of the system. And now, after we developed that, we developed another essential component for the system, which is QAR. This is our super intuitive programming language. It's a pulse level control programming language in order for you to write very intuitively the program that you want to run on your device. And then our compiler compiles it to the more complicated machine code of the pulse processor. So this is how the ease of use comes into play, because we have this super intuitive programming language that compiles to the pulse processor machine language. All right, so how does it work? So you have your quantum system. Maybe it's an array of atoms using tweezers arrays, or maybe it's a bunch of trapped ions. You connect to it our controllers, the quantum control hardware. Each one of these modules, we call it the OPX, and each one of these modules have the two elements that we discussed, the pulse processor and the analog frontend. And then they are connected through a server, what we call the QM server, which is our server layer, to the network. And anyone on the network can connect to the QM server and run experiments, run algorithms and programs on the quantum device. So when you start working with such a system, again, you connect the OPXs, the control hardware, to your setup, to your quantum system, and then you define what we call a quantum machine. So here we see 3 quantum machines, QM1, QM2, and QM3. And now you can write QA programs and run them on these quantum machines. So Ramon here is going to give you a deep insight into what you can do with the quantum machine. Specifically, is going to show examples from the AMO world, from atom arrays and ions, on how you on examples of programs that you would want to run on your quantum device. I just want to give you a feeling of how in general a QA program looks like, and how the look and feel of it is. So this is the simplest program that you can think of. Here we just want to play a pulse over and over, but play the pulse with different with a specific frequency. Let's say I want to play a pulse that's modulated with 100 megahertz, and I want to repeat it over and over. Already here you can see that with simple test equipment, let's say a simple AWG, you would have to generate this entire waveform, even though I'm just repeating over the same thing. I need to generate this entire waveform, and then load it to the arbitrary waveform generator. But with QA, you would simply write these 3 lines. So I'm writing for I, goes from 0 to 100. I'm just playing a pulse to a certain channel, and then I'm waiting 100 nanoseconds. So this actually, because I defined this channel 1 here to have a frequency, let's say 100 megahertz, the pulse, this pulse here, maybe a Gaussian pulse, will be modulated with 100 megahertz. And actually, because we have real-time oscillators on the pulse processor, as you can see here, the phase of the signal will be continuous. So actually, these pulses are not identical to one another. They start with different phase every time, because this is what you want. Say you play a Ramsey sequence, you want the first pi over 2 and the second pi over 2 to play with different phases. So this is very natural in the for the pulse processor. This is just done automatically. And again, this entire waveform is actually going to be generated from just a much shorter waveform stored in the waveform memory. Okay, then we can complicate things a bit. We can maybe loop over an amplitude of a pulse. So here you see that we're playing a pulse, but we're looping over this variable A, and we're playing the pulse times amplitude A to this channel. And then we can see that we're scanning the amplitude. Already here you can see that there is some classical processing happening in real time. Again, this entire thing is happening in real time. We're not generating this in software and then loading waveforms to the AWG. We are really doing this entire thing in real time. Then I could play 2 pulses with a wait command between them, wait T between these 2 play commands. Maybe this is a Ramsey sequence where maybe I want to measure T2, so I want to scan this delay. So here I'm looping over this delay. And as you can see, again, we're doing this whole thing in real time again. I could add frame rotation, so I could actually rotate the phase of the oscillators that we have, and I could do it based on these classical variables over which I'm looping. So here I'm actually rotating the phase with an angle that's proportional to the delay. And finally, we can do frequency multiplexing. These are just some examples. Ramon, again, is going to show you many more. But you can easily play many pulses with different frequencies. Let's say I define these elements, we call these elements atom 1, atom 2, atom 3, to have different frequencies. Then if we just play them in parallel, and let's say that I decided that this atom 1, atom 2, and atom 3 are hooked up to a single channel of our control hardware, then these pulses will simply be added together, and it's very easy to play multiplex frequencies. All right, so I think I'm going to pass it over to Ramon now, who's going to show you some cool examples from the AMO world.
Hello, and welcome to the demo part of this introduction. So I'd like to set kind of the stage for what we're doing here by going over kind of the DiVincenzo criteria for atom array quantum computers, and then talk about what I will show in that context. And in that context, what I will show is basically an example of atom assembly and a simple cpmg example that we'll take as a basis and that we will expand on just to show you the basic capabilities of our system. So let's start. So the DiVincenzo criteria for AMO is kind of the following. So first of all, you have to have a scalable physical system with well-characterized qubits. That's kind of the basis of everything we're doing here. And while that's a given for superconducting qubits and for spin qubits, for atoms and ions, that's not the case. You need to instantiate the system by loading, cooling, loading, and assembling atoms. And later you also need to address them. So you don't have cables connecting to each qubit. You actually have to arrange that with AOMs or AODs. The second stage would be to the ability to initialize the state of the qubits to a simple fiducial state. So that is typically done with optical pumping sequences, and that's not the most is relatively a simple thing to do. The third thing is to need to have a long relevant coherence time. So coherence times need to be longer than the gate time, and to do that, various techniques have been developed decades ago, and I will show one example, the cpmg protocol, later on. Then you need to have a universal set of quantum gates, of course. You need to be able to perform single qubit gates, 2 qubit gates, and even multi-qubit gates. I won't get into that today, but we will be more than happy if you would want to schedule a meeting with us, and we would show you a private demo of all these things. And it's really our bread and butter. Then you would need to also have a qubit-specific measurement capability. So that's typically done with EMCCD cameras or using fast photodetectors. And I will show a quick example of how you do readout from photodetectors, do time tagging, and use the data in real time to inform later calculations. Another sixth thing, it's not in the DiVincenzo criteria, but I think it's worth a mention here, is that once we start building systems of several dozens or hundreds of qubits, which seems to be within reach in Rydberg atom arrays, the issue of verifying the result will become serious. And the fact that quantum computing setups are using the quantum orchestration platform from a variety of systems. So we have clients in superconducting qubits, in spin qubits, quantum dots, atom arrays, and ions, means that there is a common language among platforms that will allow using similar code or porting code among different quantum information processing platforms. And that will allow a form of verification of the result by running the same algorithm on different systems. So let's start. Let's go straight into atom assembly. So the way things are typically done in atom arrays is that, well, it's one of the typical setups, is that you have a static trap array that is generated from a static trap beam, reflected from an SLM, and which creates an array of static traps where you probabilistically load atoms. On top of on this beam, you superimpose a second beam that goes through a pair of crossed AODs, and by controlling the RF signal going into these AODs, you can generate moving tweezers that you can use to assemble the array into an ordered system. And so this is what I will show you today, the way that we calculate these two signals going into these cross AODs to allow for the arrangement of the array. So the way that it's being done currently with our system is that the atom array, after it was probabilistically loaded, is imaged with a camera. And this image undergoes image processing using a separate PC or an image processing card. And the result of this image processing is basically an occupation matrix, an n by n occupation matrix of the array. So an array of Booleans indicating where you have atoms and where you do not. And this n by n occupation matrix can then be transferred to the pulse processor and written directly into registers of the pulse processor via Python, our Python API. And that doesn't take long. I mean, for a 10 by 10 array, it takes less than 5 milliseconds. And for larger arrays, there are other faster ways to transfer data to the OPX. And we could discuss about that later if people will have questions. So that's the basic setup. So here we see an example of Pascal. We have a collaboration with them of a typical arrangement of atoms. Okay. So the basic idea of the way we do assembly is that each atom in a single row is assigned an oscillator, or a pulsar core that Jonathan talked about, and that will effectively be a single tweezer. The tweezers, several of them in parallel, we will set the frequencies and phases to correspond to the position of the atoms. So every atom on a single line will have a tweezer associated with it, and then we will generate on the fly dynamically a multi-tone chirped waveform that will be sent to the vertical AOD, and a simple single-tone waveform that will be sent to the horizontal AOD just to select the row that we are currently assembling. And so in such a fashion, we will assemble the array row by row, and we will see now how that goes. So before we actually play this dynamical multi-tone chirped waveform, we need to do some classical calculations, such that in the form that Jonathan alluded to. So we need to first assign the tweezers to the atoms. So every atom has a position on the row that corresponds to a certain frequency, an initial frequency for the tweezers. So we need to set that. We need to also set the phase of this tweezer, because you want to avoid the interferences. Then you need to calculate the pulse length. So in the way that we do arrangement, the pulse length is dynamically calculated on the fly to be optimal. So if the arrangement involves simply moving all atoms one side to the left, the pulse will be very short. And if there will be a very far away atom that needs to move quite a lot, the pulse will be longer, because everything will be limited by the maximum chirp rate, the maximum velocity that we allow the atoms to move. And so for each, so there is a common pulse length for all the atoms, for all the tweezers. And then for each tweezer, we calculate a separate chirp rate. So all atoms start and finish their movement at the same time, but each one moves at a different velocity. And so at the end, we will set the tweezer frequencies and phases. I will go into the details of what's going on into all of these functions. And these functions are written in such a way here, just to show you that you can use macros, you can use functions to group code of qua, and ease up, the way that code looks when you're working. So after you've calculated everything and you have the length of the pulse and the chirps and everything, you start simply by ramping up adiabatically the power of all these tweezers. So first you ramp up just the row selector pulse, just to select this particular row that we are working with. And at the same time, in parallel, we have here a for loop that goes over all the tweezers, and we're playing this ramp for all these individual tweezers. So now all of these play commands, all of these pulses have the same output port out of our OPX device. So they will be added at the output port, and you will have a single channel, that has a frequency multiplexing of all these tones. So all of these tones will be ramped up together, and it will be at the same time as the row selector tone. After we've done that, everybody is on. We will chirp, and that takes another 3 lines of code. The row selector does not chirp; it just stays for a duration, this dynamic duration, which is the tweezer move length. But the individual tweezers will again play a pulse with this length, but each one will have its own chirp rate, so that each atom moves with a different velocity. After we've done moving all the atoms, we will ramp down, which is basically exactly the same thing as we have here, just with a negative sign for the ramp slope. And then we will adiabatically ramp down the power, and the atoms will end up in the traps of the static array generated by the SLM. So again, just to recap, all atoms move together with a common pulse length, but with different velocities or chirp rates. All atoms start and reach their target destinations at the same time. The pulse length is calculated by the pulse processor. The atom which is further away from its target moves at the maximally allowed velocity. So the way we wrote the code is, and of course you can change it, is that you set the maximum allowed velocity, and then you figure out which atom is the farthest away from where it needs to be, and then that sets the length of the pulse. So to do that, so this is some lines of code of the functions that I've shown you before. So to calculate the detuning of each tweezer, we simply do a for loop, and we assign values into a vector, a qua vector. That is simply the difference between the target frequency and the original tweezer frequency. Then we take this vector, and again, in real time, we have a maximum function that calculates the maximum of a vector. And then the length of the pulse is calculated simply as the maximum detuning, this max detuning variable, divided by the maximum rate. And then we do another for loop where we calculate the chirp rates for all tweezers, which is simply the detuning of each tweezer divided by the length of the pulse. So then the maximum detuned atom will simply have the maximum rate of chirping. Okay? So now I want to show you the live example on my oscilloscope here. So in this example, follow closely, the yellow trace or the orange trace will be the multi-tone pulse that we sent to the vertical AOD, the multi-tone chirp pulse, and the purple one is the FFT of this pulse. So let me go on into my code. So this is my PyCharm editor. Qua is hosted within Python. We have all these functions that I showed you before. So the calculation of the chirp rate is this for loop. I'm not hiding much. So this is the whole code. Here it's just simply declaring variables. And here is the code that I've shown you before. The whole thing is 137 or so lines of code. It's not very long. It arranges a single line, but it's just an example. So if I now bring up my oscilloscope, my dear oscilloscope here, I hope you can see it, and I will run this, we will see the chirped pulse. Let's see. Here we go. So the green one is the row selector AOD. It's not very interesting. It's a single frequency, but it's ramped up and down. And the yellow one is the, as I said before, the multi-chirp pulse. Now, if I zoom in, we can see the FFT, and if I move my, I scroll my scope, you can see it moves. Now it will take ages because I need to zoom in. So what I prefer to do is to basically, I prepared another example here where I slow down everything. I put everything inside a qua loop that loops 1,000 times. And so that will allow us to do everything in slow motion. Let me run this. Okay, so it's loading. The green one is not so interesting. Let me switch it on. So it's compiling and running, and here you can see the atom location list. So this is where I said that the atoms originally are, and here you see that the atoms, the tones are chirping. There are no skirts on these FFTs, indicating that there are no phase jumps and no dead times, and then it's done. I can remove, for example, this, make a hole here in the target list. So instead of having 9 atoms tightly spaced, I want to have a hole here, so I can run it again. And so if I run it again, you will see that the arranged array will have a hole in the second spot. Okay, here we go. So it's chirping, as you would expect. There are only 8 tweezers now because I removed one. It automatically finds out, and that's it. There was a hole, and it's gone. Okay, so this is the atom arrangement. So I can also show you, for example, where is it? I can trigger it, and I can show you that. So here I've shown you before that the chirp length was something. And if I change the position of the atoms, for example, so here the length was this, so it took 1, 2, 3, 4, about 4 milliseconds. But if I add one atom here in the original list, the pulse length will be much shorter, because now we will need less moves to arrange this array. And so you will see. So it reaches here for this. I'm sorry, I did not trigger it. I'm sorry. I did not trigger my scope. So it's, and it takes exactly the same amount of time to compile everything and run it. When you will be running this in real time, you will be able to trigger it. Okay, so you see now it's much shorter, just because I've added a 1 here. Okay, let's go back to the presentation and let's show something else. Let's minimize this for a moment. Okay, so we said we need to instantiate the atoms. We've assembled now. I hope you believe in that we can assemble an array of atoms. You have multiple tweezers that you can use at the same time. Writing the code is very straightforward. Looks like any high-level programming language. Optical pumping we will skip because I wanted to show you something more interesting. So let's go into an example of dynamical decoupling. So a simple cpmg pulse, here we see cpmg 5, is of the following form. You have a pi/2 pulse on the x-axis, followed by a wait time t/2, a y pulse, and a wait time t/2, and this is repeated n times. And at the end of this, we have another x gate. And so, in order to do this it makes perfect sense to use a pulse processor for this, because here the constructs are very limited. You only have a limited amount of actual pulses that you want to play, and everything else is something that you can program with the pulse processor. So how does the cpmg code looks like in Qua? That's it. So basically, here we define this dt, this spacing between pulses. Here I define the number of cpmg pulses. And I have here my Qua program. I declare an integer I. I first play my first pi/2. So basically I do it in power. So I send AOM1 my pi pulse, and I multiply it by half to have half the power to have a pi/2 pulse. And then I'm doing a for loop, where I'm scanning I from 0 to the number of my cpmg pulses, so to do 4 iteration of this thing. And here I'm going to wait dt over 4, dt over 2, sorry. And then I'm going to do a frame rotation. I'm going to apply a pi/2 phase shift, so that I'm now working on the y-axis. And then I'm going to play my pi pulse. But because I did this pi over 2 phase shift, I'm now performing a y gate. After that, I'm doing another weight dt over 4. And then at the end, after this for loop, I will play another x gate without applying a frame rotation. So that's it. So let's see how it looks like on the code here. So I will trigger this. Let me change the trigger to be 2. Okay, so if I'm running this now, this is the code. Okay. Oops. I was not zoomed in enough. Okay, I can remove the FFT. There's no need for this now. And let's zoom in a little bit. Sorry, I need to show you the screen. I forgot to show you my oscilloscope. So here you see, basically, I can trigger this again, run it again. So the yellow trace will be this AOM1 that I'm showing. And I'm also plotting, I'm also added here some helper pulse to which I'm doing nothing, just so that you can easily follow the phase. So you see here, at first the phase is the same. And then I'm waiting some half period. I'm doing a pi over 2 phase shift, and then playing, and then waiting twice this time, and doing another one, and then another pi over 2 phase shift, and playing another one. And this is my cpmg 4, basically. So here, everything, again, as Jonathan said, is generated on the fly. And I'm not saving any, actually here, and I put here a 1 megahertz tone just so that we can follow the phases. But this can be any frequency. It can be 100 megahertz or 200 megahertz. And anything, and so it doesn't take any way for memory to generate this. Here I'm doing constant pulses. There's no amplitude. So basically I just need to provide the amplitude of these pulses and the length as numbers. And then everything is generated on the fly by the pulse processor. So for example, if I were now to, instead of doing a cpmg 4, I would do a cpmg 4 million, and I would change my oscilloscope to be 1 second, and run it. I will be able to do a multi-second pulse with 4 million cpmg pulses, and it would take the same amount of time to compile and same amount of time to execute, only that this time I'm having 5, 6, almost 6 seconds of pulses. Yeah. Okay. So this was that. Let me show you what else I prepared. Let me minimize this. Okay. Another thing that I can do, as Jonathan showed, is I can change the amplitude on the fly. Let me put this back into there. I can change the amplitude of the pulse. I'll declare another variable, I'll do it in a second, called amplitude. And for every iteration of this for loop, I will increase this amplitude by some 1 over the number of cpmg pulses, so that it's at the end reaches a reasonable amplitude. So let me do that. So here I've commented it, and I've commented it here, and here I will just multiply this by this amp, and I run it. Oops, sorry, because I did not, let me do that again. I did not zero in my thing. Here we go. So you see, I have the same pulse here with an increasing amplitude. Yeah. Another thing that I can do, let me go back to my code here, is, I hope you have the time to see that amplitude is increasing. Another thing I can do is I can, instead of doing a simple pi pulse, a simple flat pulse, as you've seen here, I can do a Gaussian pulse. Okay, let's go back to the code. I just changed here. I've prepared this waveform in advance. Let me also change the frequency to be 100 megahertz so that you can actually see something and not do it like this. Okay, I'm running. So instead of a simple pulse, I'm now doing a Gaussian pulse. And as you can see, I have a Gaussian, a train of 4 Gaussian pulses, and the amplitude is increasing from shot to shot. And here I only had to store this waveform of a Gaussian once. This thing is done in real time, the change of the amplitude. What else do we have here? I can change the duration of the pulse. The duration of the pulse, even if it's not a constant pulse, even if it's a Gaussian, as in this example, the pulse processor will do a third order Lagrange interpolation in real time. Let me show you that. And we'll stretch the pulse. So basically, then I can dynamically change the duration. I can say duration equals I plus 1 because I don't want it to be 0. And I multiply it by 250. So every iteration of this for loop, the length of the Gaussian will be different. So let me run again. And let's see. Here we go. I need to zoom out a bit because it became longer. And so you see, so now I have 4 different pulses with 4 different amplitudes and 4 different durations. And it took no more memory. It's still the same Gaussian pulse. It's still phase coherent, of course, and so on. Yeah. Okay. What else do I want to show you? Let's see what I have in my slides. Yeah, I want to show you time tagging. So let's say now you've done that and you want to do some readout. Let's say your readout is using fast photodiodes. Okay. So what we can do is we can declare 2 variables. One is called time tags, and it's a vector of size 10, for example. And the other one is called counts, and it's simply an integer. And then we're doing a measurement pulse, which it doesn't have to have any laser pulse associated with it, but you might want to. So the readout pulse can be either an empty pulse or it can be some laser excitation or anything. We're going to do it on a separate AOM. And then we're using the time tagging construct to open a window of length. In this case, it's 1 microsecond. The units are 1 nanosecond, but it can be anything. It can be tens of milliseconds or more. And it will provide, and it will listen in on the port of the OPX, and it will time tag any signal, any trigger that comes in, and it will sum up the counts. And then you can later do histograms and whatever you want. And what I'm doing here in this example is that I'm going to use this counts variable, and I'm going to do a conditional pulse based on it. So because I have nothing connected to my input, certainly not a fast photodiode, the counts will be 0. So what I've done here is that I've said, okay, if counts bigger than -7, then play this pulse, a constant pulse on channel 2, okay? And so, and if it will be 0, it won't play. So basically, I'm able to do a real-time measurement, and based on the results of these real-time measurements, I can do, binning, open a window, do binning. I get also the time tags, and based on the result of this measurement, I can continue on in my sequence and do conditional branching, and I can use this value, to put it into wherever I want. It can be the amplitude, it can be whatever. So let's take a look at that. So here I uncomment this part. Okay, and let me trigger this again, and I run it. See, so there's nothing coming into my OPX, but you can see that, so I've played one before, one of these AOM before, and the other one is being played here at the end. Where is AOM 2 here? Yes, exactly. But if I were, because I'm playing this readout, so I'm doing this readout at the beginning, it should be at the end. I could move this align command, over here, so that everything is done when it should be. So align is our way to align time frames among different threads, among different pulses. You see? Now, so this 1 megahertz thing is simulating a readout pulse, and then I'm doing the measurement, I'm doing the processing of the time tagging, and then because I got 0 because I had nothing connected in, and then so 0 is bigger than -7, so I play this pulse. If I were to say, okay, the threshold would be 0, and I were to play this, then I would not have that final pulse. Okay, let's see. Exactly, I have the measurement pulse, but I have I don't have this pulse because I did not cross the threshold. Okay, let's bring it back to -7, and I want to show you one last thing, which is our simulator. I'm going to close my scope. I won't need it anymore. And instead of executing all these things on my actual machine, these are the lines of code to do that, I'm going to run them on a simulator. We have a simulated environment of the pulse processor that you can use to debug your sequences, basically, offline, kind of, when you're not in the lab, or before you want to run anything, and if you don't have an oscilloscope. And so this allows you basically to get all the channels from the OPX into your Python environment, and this is a bit accurate simulation of the pulse processor. So if there is some dead time due to calculations or anything like that, it will be represented by the simulated pulses. And this is a very useful tool, of course, to debug pulses and to be able to work on constructing complicated sequences. So that's it for me for now. I don't have anything left. Thank you. I think it's a good time for questions. Maybe we have a few minutes left. If anybody would like to chirp in and ask something, I'll be happy to answer. So the questions I have here: what's the feedback latency? Can a locking scheme be used? So yes. So the latency is on the order of 200 nanoseconds. There isn't. It really depends on what exactly you want to do. And yes, we've managed to do, for example, PID or pound-Reverhall kind of loops. Everything written in Qua, in a high-level programming language, and have a bandwidth of megahertz. So that's very nice so that you can use the inputs and outputs to do very fancy feedback loops in real time, and not have to solder a single component. You can do everything from a programming language. The second question I have here is, can the QMs be far away from each other? So it depends. If you want them to all be coherent, you can connect them via network. They can be a bit far apart, but it really depends on what you want to do. So each one comes with you need to have one single server connecting to both of them, and the cable connecting the PCI Express connecting the server to the OPX cannot be too long because it transfers a lot of data. But there are ways for you to have. You can if you want, you can get two OPXs and put them in different labs. You set and you can manage that. Yes.